Okay, I guess we can go ahead and get started. Welcome to the Introduction to Mathematical Thinking DeCal. My name is Suraj. I'll be the instructor for the course. This is the second time this class is offered, and I'm really excited that you've all decided to take it. So how today will work is we'll go over sort of why this class was created, what some of the logistics will be, so what some of the topics will be. I have a few questions to ask you, and then towards the end, we'll go over this cool application of discrete math topics that you're not going to be tested on or anything, but I think it's interesting. And I didn't know too much about it until last night, actually. And I think you'll be quite surprised by it. Okay. So the very first question, I guess, is why does this class exist? Hold up. That's fine. Okay. So, yeah, why does this class exist? Okay. And as I mentioned, this is the second time this class is being taught. I originally came up with the idea, I believe, in October or November of 2017. So the idea has existed for quite a while now. And the first reason, mainly, is that CS70 is hard. I mean, you've probably heard this from your peers. And the idea behind this course is that you take this a semester before taking 70, and will expose you to a lot of the ideas that are taught in 70 at a more friendly pace, so that when you do take 70, in the summer or in the fall or wherever or whenever, a lot of these topics won't seem as foreign to you. And you'll have experience with them. I'm not saying you're going to be masters at everything in this course, but you don't need to be, because you'll have heard of a lot of these topics. And then when you go to 70, they'll seem a lot more inviting and less foreign. Does that sort of make sense?
Yes.
Cool. Another reason this class exists is because math, especially discrete math, is fun, right? And we sort of just want you to feel the same way. And we'll look at a lot of cool applications of things that aren't necessarily taught in 70, especially towards the end of the course, but they're nice applications of the material we'll see at the beginning of the course, and these things are just fun. Okay? And in an ideal world, we would allow as many people to take this course as they wanted to, and we could have non-CS and non-math students take this course for fun, but due to the restriction of the size of this room, we sort of have to prioritize who we let into the course. Okay? As you know, this is a 2-unit DeCal, but with that being said, the best way to learn math is by doing math, and so we'll make you do homework weekly, and it will be graded on GradeScope just like in any other problem set class. However, homework is graded on completion and effort as opposed to correctness. So that sort of takes the worry off of you from, spending hours upon hours making sure that every single answer is right. It won't be like that. The goal is that you attempt each of the problems to the best of your ability, spend, maybe 3 hours on it, and once you've had enough, you can sort of submit that, and that should be good. And the goal is, by doing the homeworks each week, you'll engage with the topics that we sort of cover in the course, and even extend some of the ideas by doing themselves in your homework. Okay? This is not the DeCal to take for an easy 2 units. Okay? So if that was your intention for this class, you're probably in the wrong DeCal. I'll tell you that right now. I'm not saying it's impossible to pass. It's certainly not impossible to pass. I don't want to make it seem like nobody's going to pass. But it's definitely not the DeCal to take to just sort of sit there and get 2 units from. Is that sort of clear?
Yes.
Cool. With that being said, we know that most of you are probably in some combination of 61A, 61B, and EE16A, EE16B. And so in designing when sort of things are due in this class, we've scheduled around those midterms because we know, obviously, those will be your priorities. Okay? Sound good? Okay. So now I want you to get familiar with the other people that are helping teach this class. I've already introduced myself. A little bit more about me. I'm a third-year EECS major from Canada. I like the Lakers, I guess. We're getting AD soon. Yeah, that's a bit about me. The TAs that are here, do you want to introduce yourselves?
I'm Jay. I'm a freshman here, trying to major in CS data science. And I like the Clipper assignments.
I'm Alexia. I'm a sophomore, and I'm a CS major. And I don't know, I'm a Gemini, yeah.
I'm Savnik. I'm a freshman. I'm intended CS and statistics major. And yeah, I like math. You can ask me math. I really have.
Cool. And so 4 out of the 5 TAs that we have this semester, so everyone except for Adele basically, all were students in this class last semester. So they've worked with me in implementing feedback that we had from students last semester and tweaked the course in various ways just to optimize the experience for all of you. Okay? And all of the office hours and things like that are listed on the website, which I'll project in just a second. But feel free to ask any one of us basically anything, whether it's about this course or not. Sound good? Cool. Ooh, not the eraser. Okay, so let's take a look at the syllabus. And this is a new class, so this may change a little bit, but for the most part, this is sort of the order in which we'll cover things. So starting next week, starting on Thursday and all of next week, we'll talk about what the definition of a set is and what the definition of a function is, and how to formally define various set operations. Okay, and it may not be the most exciting thing, but a formal treatment of these topics is necessary as we cover the things later in the course. Okay, we'll then spend 2 classes talking about propositional logic, which will lead nicely into formally covering various proof techniques. So we'll cover things like direct proofs, proofs by contradiction, mathematical induction, and that's sort of the bread and butter of what this course will be about. Okay, and after that point, we will sort of spend the most of the rest of the course proving various things just about different areas of discrete math, if that makes sense. We'll then spend 3 classes talking about number theory, modular arithmetic, how to find modular inverses of things. We'll then talk about counting techniques, so permutations, combinations, probably a bit more in depth than the SAT questions that you did. But that's okay. We'll talk about things like Pascal's triangle and these things called combinatorial proofs, how we can make proofs that are different than just the standard algebraic proofs that we've done. We can talk about proofs in an argumentative type of way. Then we'll expand on these counting techniques and start talking about them in relation to polynomials, things like the binomial theorem and Vietta's formulas, and different ways to and different properties of binomial expansions and that sort of thing. And then the last 2 weeks, I'm not entirely sure what we'll cover yet. What's on the board is sort of what we've covered last semester, but that is still subject to change. This semester, the course is actually a week or 2 longer than it was last semester because I've decided to start it 1 week earlier. And also there aren't things like Veterans Day or Thanksgiving. Those, we have quite a few long weekends in the fall, but those don't really exist in the spring except for President's Day and then all of spring break. So we have quite a bit more class time this semester, so at the end I'm not entirely sure what we'll cover, but it'll be something interesting hopefully. Any questions with the syllabus and what we aim to cover in the class? Yeah?
How much do we cover CSM?
What was your name?
Raphael.
Raphael. In terms of 70 material, so the goal of this class is not to exactly cover what is exactly in 70 because you're going to take 70, right? The goal of it is to cover a lot of things that are related to the material in 70 that will help you when you are in 70. Does that sort of make sense? Yeah. With that being said, a lot of this is almost directly covered in that class, right? Especially all of this content will almost directly translate to things you may be tested on in future courses like 70. The content towards the end, some of it is definitely included in 70, but a lot of it is sort of tangential and isn't necessarily directly covered in 70, but it will help you in terms of thinking of that sort of problem. For example, like the binomial theorem itself isn't covered in CS 70, but when you get to the end of 70 and talk about binomial distributions, that's very related to something you would have seen in this class. But we're not doing any probability here. Any other questions about the syllabus? No? Cool. So a bit about the logistics. So, of course, class will be held on Tuesdays and Thursdays from 3:30 to 5 right here in this room. I know that this time conflicts with EE16A. Show of hands, how many people are in EE16A? Okay, so a decent number of you, but that's okay because EE16A is webcast and also doesn't have any in-class examinations, whereas we will have all like all of our testing will be within this time period. EU16A doesn't have anything within this time period. And 16A is webcast, so I think that's okay. And I mean, you've decided to still show up, which means you're okay with it as well. Attendance is mandatory. We'll be having a Google form every class, and you'll sort of have to sign into it. And it will ask for your Berkeley authentication, so you can't you're not going to send your friend your Berkeley email password. I mean, maybe if it's your close friend, I don't know. But don't do all that. Attendance is mandatory, and just let us know in advance if you can't make it. We're reasonable with this sort of thing. If you're going home to see your parents, or going to Coachella, or whatever, just tell us, and it's fine. But try your best to be here. With that being said, I will try and webcast all of it. I'm sort of recording audio and video off of my iPad right now. I'm trying a new setup this semester because before I, recorded from my laptop and it just took way longer to export things. So I'll see how well this works and how well the audio works. But if not, I'll try something else. Maybe get a microphone for the clip. I don't think this room is set up with all the webcast technology, and I don't think they're going to do that for DeCal. Anyways, sounds good? Okay. We also have 3 hours of office hours each week. There's Monday 3 to 4 p.m., Wednesday 7 to 8 p.m., and Thursday 2 to 3 p.m. They're all in that SOTA third floor alcove, so 341B. All of this is all on the website as well. We're going to use Piazza, and I highly encourage you to ask questions on Piazza and engage with your fellow peers in this course on Piazza. It'll be a good resource, just as I'm sure you've become accustomed to in other classes like 16A. Of course, the course website, you've probably all seen it before. That's where all the content, including these webcasts or textbook reading, that sort of thing will be posted. I guess we can take a look at it right now. Okay, I mean, you've probably all seen this before. But yeah, our office hour information is there. Piazza links and Gradescope links will be there, but I'll also email that out to everybody and manually invite everybody. All of the resources for the course, week by week, will be posted here. So, I mean, the slides for today will go under course overview. If the video will also go there. The reading is sort of linked here. You can click this. It'll take you to this online textbook thing that was made just for this class. The beginning, for example, chapter 1 and chapter 2 is all complete. The rest of it is still in progress, but I hope to have it done by the time we reach that part of the course. Okay? And this is a very, very new resource. It's still constantly being updated almost every day. So if you find any errors with it, I'll have a thread on Piazza about it. And feel free to post if you think something is not explained that well or you think there's a typo, and we'll fix it immediately. Does that sound good? Okay. Okay. So now let's talk about everyone's favorite topic, how your grade will be determined in the course. Okay? As I'm sure you're all aware, it's pass, no pass. I'm not out to fail you. It would hurt me if I had to fail you. So we're trying to make it not as easy to pass as possible, but as reasonable as possible within the confines of this being a 2-unit decal and knowing that you all have other courses to worry about. Okay? So last semester, how it worked was there were weekly homeworks and then a midterm and a final. Okay? And by final, we mean it wasn't during the regularly scheduled final week. It was just the last sort of meeting that we had in this class. Okay? But that didn't work for a couple of reasons. Primarily, the people in this course are probably freshmen and sophomores, right? And a lot of you will be taking classes like your R1A or your R1B or some sort of breadth class. And a lot of those classes have their final paper or whatever due in the last week of classes, and people didn't it's not your number one priority, this exam for a decal, right? And by spreading it out into 5, not bi-weekly, they're a little more spread out than that, but spreading it out into 5 quizzes ensures that you're constantly staying up to date with the material without making any one of the quizzes weigh that much, right? So if you have a bad day one time, you weren't feeling the material that well, that's okay because there's 5 quizzes and they're each only worth 12 points out of 100. Okay, so the quizzes total for 60 points, and no one of them is worth too much. Is that okay? Cool. Then there will also be weekly homework, which is graded on effort. I don't know exactly how many there will be. At least 8, though. So if there are 8, they'll each be worth 5 points, as you can see. In terms of quiz drops, homework drops, not entirely sure how many or if they will exist at all. So for now, attempt your best in completing every homework and attending every quiz. But if you have any other circumstances, feel free to let us know, and we're pretty accommodating. Is that okay? Yeah.
For our 5 class, 3 class quizzes, so like during the weekly homeworks, is it like just if you're able to like do the weekly homeworks, will that be like allowing us a little bit of preparation enough for the quizzes, or do we like dedicate a lot of time for?
No. So that's a great question, and I'm about to talk about the quizzes in just a second. If you're staying up to date with the homework, and of course coming to class, engaging, looking at the solutions once they're posted, and maybe review all the notes you took or just skim through the textbook again, that should be enough preparation. Like, it's not designed for you to have to study 10 hours each time we have a quiz. Does that sort of make sense? Okay. As it says here, homeworks will follow a Friday to Friday schedule. So they'll each be due Friday 11:59 p.m. on Gradescope, and the next one will come out either sometime Friday night or Saturday morning, or sometime during the day Saturday. Is that clear? Due every Friday 11:59 p.m. on Gradescope. The first homework is coming out this Friday and will be due next Friday. And there will be technical material on it, mainly stuff that's covered on Thursday. But there will also be things like tell me about yourself, what other classes are you taking, that sort of thing. So any questions about how the course is structured? Yeah?
Not really about how the course is structured, but I had another question on how do we get the units placed into Cal Central?
Good question, and I'm about to talk about that in just a bit. Okay. So any other questions about how the course is structured? Okay, so we have 5 in-class quizzes, and the dates for 4 of them are pretty much already set in stone. Okay, so the second quiz will be on Thursday, February 28th, the third on Pi Day, 4th on April 9th, so it's the week after spring break, and Tuesday, April 30th, which I believe is the second last week of classes, or it might be the last week, I'm not entirely sure. Okay, the later 4 quizzes, I've already ensured that they don't occur immediately before any 61A, B, 16A, 16B exam. So you can sort of dedicate a little bit of time to this, right? When 61B midterm 2 is coming around, you're probably not going to spend much time on this. The only one that we haven't entirely decided the date for is the first quiz. It'll either be on Tuesday, February 12th or Thursday, February 14th, okay? And on the attendance form that I'm about to display, I will sort of ask you all what your thoughts are on which date you'd want, okay? So the reason we're not sure is because the add drop deadline, not the one just for without paying the $5 or whatever, the absolute add drop deadline is February 13th, okay? So if we have our quiz on February 12th, it will allow you to do the quiz before the drop deadline. So if for whatever reason you decide you don't want to take the class anymore, you're able to drop it at that point, okay? But the downside is it's the day after the first 61A midterm. 61A midterm 1 is on February 11th. Okay? On the other hand, we could do it February 14th. It's one day after the drop deadline, and it's a few days after 61A midterm. So you can sort of only worry about it after 61A's midterm 1. But you won't be able to get your results in time for the drop deadline. With that being said, I find it highly unlikely that you would take the quiz on February 12th and it would be graded on February 13th, right? So it would be more of a litmus test for yourself to see whether or not you want to stay in the class. My personal suggestion would be for February 14th, just because I feel like February 12th is a little too soon. As well, the first quiz won't be too demanding either way. It will probably be easier than the quizzes later on into the course, just because we haven't covered as much material. There's not as much that we could potentially test you on. But whatever is comfortable for you. I'm 100% okay with either of these 2 dates. Any questions with that? Yeah?
Will quizzes be like cumulative or localized to that stuff, like material we study between 2 quizzes?
So good question. They will primarily focus on the things we just covered, but if there's an application on the concepts that we just covered to something that was earlier in the class, we can also include that. But if you study for quiz 1, then when it comes to quiz 2, you won't have to restudy quiz 1's material. Does that sort of make sense? Okay. So any questions with this? And in the attendance form I'm about to put up, you will have the option to vote for whichever option you can. Okay? Actually, right before you fill that out, let me add an option for no preference. If it doesn't matter to you, then you can sort of click that option as well. Let's see. Okay, so there's a no preference option as well. Also, quizzes will be 30 minutes long, and they'll be held at the start of class. It seems like there's a class right before us. I'll try to start as close to 3:40 as possible, but if it ends up being 3:45, it's not the end of the world. Okay, and there'll be half an hour in class. Do you have a question? Yeah.
Yeah, so for like visitor, like how will they be posted like the day of?
Ideally, yeah. If the system that I'm trying out works well, then it shouldn't take very long for me to upload it. But worst case, it would be the day after. But almost certainly, I have quite a bit of time on Tuesdays and Thursdays after this. I should be able to upload that. Good question. Okay, so take a couple minutes to fill out this attendance form. And again, it'll ask you for which date you prefer. And just another question like, how's your week been? So in terms of getting units and how enrollment will sort of work. So if you don't fill out this form, meaning you're not here right now, you're going to be dropped from the class. Unless, it doesn't really make sense to tell you that because you're here. So I don't really know who I'm speaking to. But to those who were accepted and aren't here, which it seems like there are roughly 10, 12 open seats, those students will be dropped. And we have a wait list of over 30 students. So some of those will be shifted into the class. Okay? And so if you fill out this form, you will receive an email later this week. It might be as late as Friday, which is February 1st, with your student-specific enrollment code. So there's a global CCN for this class. I don't know what it is off the top of my head. But if you try and enroll in the CCN on Cal Central, or even if you go to CS 198-087 and try to enroll, it'll say you need a student-specific enrollment code from the instructor. So I have 100 student-specific codes. So what you'll have to do is go into Cal Central, type in the CCN, and then also type in your student-specific enrollment code. Okay? And everyone will be emailed their own personalized code, and you sort of enroll in that. Okay? If you came today and you decide that you're no longer interested in taking the class, please email me as soon as possible so that we can let students in off of the wait list. Is that okay? And again, also if you've looked at the syllabus and you decided, a lot of these topics may seem familiar to me, that may be another reason to potentially decide not to take this class because there are other students still interested in taking it. And if you have any questions as to whether or not you think you should be in the class, you can feel free to email me or the DeCal email. Is that okay? Cool. Okay, so for the rest of today, what we'll do is we'll look at this cool application of polynomials and modular arithmetic, and I think the result will be pretty interesting to you. Okay, we might end a little early today, which I think is okay. Sound good? Okay. So let's get right into it. Okay, so a polynomial, and don't worry too much about writing any of this down, because a lot of any technical terms we talk about will be formally defined later on in the course. This is just for fun. A polynomial is a function of the form f of x is equal to a sub n x to the n plus a to the n, a sub n minus 1 x to the n minus 1, where n is an integer, right? So it's a sum of integer powers of x. Is that okay? Cool. And you may or may not have seen this fact explicitly before, but a polynomial of degree n can be uniquely determined by a set of endpoints. Okay? So, for example, if we have these 2 points in the plane, those are 2 points, so they uniquely determine a polynomial of degree 1, which is a line, right? Y equals mx plus b. But if I only had 1 point, so for example, if I only had this, there are infinitely many lines passing through that point. Is that clear? just as if I had, I don't know, 3 points, there's exactly one polynomial of degree 2 passing through those points. Okay? And it might look something like that. I mean, my drawing's pretty bad, but whatever. You get the idea. There's only one polynomial of degree 2 that passes through those points. But if we're looking at, if we only had 2 of these points, there are infinitely many polynomials of degree 2 that pass through these points. And I mean, my drawing's not the best for that, but you can imagine, you can vary the width, and you'll still have a polynomial of degree 2 that hits those 2 points. It's a little easier to visualize with 2 points in the degree 1 case, but the idea is the same. To interpolate, a quadratic polynomial, you need exactly 3 points. Is that okay? So the general idea is, a polynomial of degree n can be uniquely determined by a set of n plus 1 points. And that word I used, interpolate, is the process of starting with a set of however many points and finding the function that exactly passes through those points. It doesn't necessarily need to be a polynomial. For the purposes for us in this class, we will probably only look at polynomial interpolation, but there are other forms of interpolation, like sync interpolation might be something you'll see if you're in EE16B. Is that okay? So the process of finding that function is interpolation. Whatever. Okay? So everyone's okay with the fact that you need n plus 1 points to uniquely define a degree n polynomial. Sounds good? Okay. So let's take a look at something that may or may not contradict this fact. Okay? So let's play a game, and I want to interact with you. Think of any polynomial with non-negative integer coefficients. So all the coefficients are, positive integers or 0. Okay? And just to make this more interesting, make it so that it's degree 2 or more. Okay? So I just take a second, think about a polynomial that fits this, criteria, and then in a second I'll ask for a volunteer. Okay, does anyone have a polynomial? Sure. First of all, what degree is your polynomial?
5.
Okay, so in theory I should need 6 points to guess this polynomial. Right? Okay, what's f of 1? I guess I should have told you, you'll have to do a little bit of calculation, but I don't pick x to the 3,000 or something like that.
10.
F of 1 is 10. Can you evaluate f of 10 or no? Or f of 11, sorry. F of 11.
I can do F of 10.
No. F of 11, I need it.
Oh, no.
Okay, can someone give me an example with numbers that you can do relatively quickly, like either on your phone calculator or mentally?
I can open Desmos. I got this.
Okay. Yeah, let's make it interesting. Give me f of 11. Okay, in the meantime, does someone else have another example they want to try? It'll be fun. Polynomial, non-negative integer coefficients.
Okay, I got it.
All right, this is f of 11, right?
F of 11, is 1127390.
Okay, 1127390.
Yeah.
Okay? That's it.
Yeah.
Okay. Was your polynomial 7x to the 5 plus 3x?
Yeah.
It was, right? Just so you know that I didn't text him before class, be like, yo, pick this polynomial. Someone else, give me an example. Sure. Well, okay, so don't tell me it. What's f of 1?
50.
What's f of 16?
Oh shit, I just did okay, wait.
fine. We can wait. So you said f of 1 is 15.
Yeah.
Okay. Find f of 16. Is it a big number?
Yeah. So
That's fine.
5, 5,
Okay.
1, 7, 8, 4, 0.
5517840.
Yeah.
And f of 1 was 15.
Yeah.
And what you gave me was f of 16.
Yeah.
Your polynomial was 5x to the 5 plus 4x to the 4 plus 3x to the 3 plus 2x to the 2 plus x. Right?
Nice.
Okay. So you're probably wondering how is this possible? Right? Okay. Let's take a look. So there's some background information we need before we can sort of understand what's going on here. So how many people have heard of, writing a number in binary or, base 8 or base 16? Potentially, right? And you always hear that, deep down under the hood in the computer, everything's written in binary, which is just base 2, right? In our regular, form of arithmetic, everything is base 10. And the reason that is because we take our digits and use those as coefficients when we multiply various powers of 10, right? For example, if we take 1344, we can write that as 1 times 10 to the 3 plus 3 times 10 to the 2 plus 4 times 10 to the 1 plus 4 times 10 to the 0. Does this sort of make sense? Okay. And now if we instead want to write this number in base 6, right, we would need to find numbers such that a times 6 to the 4 plus b times 6 to the 3 plus c times 6 to the 2 plus d times 6 to the 1 plus e times 6 to the 0 adds up to 1344. Is that clear? And the reason I started with 6 to the 4 is because I happened to verify on my own that 1344 lies between 6 to the 4 and 6 to the 5. So I know it's going to be 6 to the 4 plus something. Is that clear? Okay. And it turns out that there's a standard process that we can use to find these coefficients, and we can do so by repeatedly dividing by b, in this case 6, and taking the remainder. Right? And you've probably all seen that percent sign operator in Python, right? Modulo. And we'll talk pretty in depth about modular arithmetic later in the course, but for now we don't really need to talk about all that. All we need to know is that percent sign means remainder when you divide by. Is that okay? So recall, percent sign is remainder when divided by. Okay, so what we want to do is find numbers a, b, c, d, and e such that I can write out this expansion. I have a question for you. What's the largest possible value of a, b, c, d, or e? Why is it 5? Exactly. In binary or base 2, the only possible digits are 0 and 1. In decimal, which is base 10, the possible digits are 0 through 9. And I don't know if you've seen the number representation format for colors in hexadecimal as opposed to RGB. That's the largest possible digit is 15. And the way they represent digits 10 through 15 is by using the letters A through F. Is that clear? So in base 6, the largest possible digit is 5. So any questions with why the largest possible digit is 5? Yeah?
Why did we choose base 6 again?
Oh, I just picked an arbitrary example. Okay, we still have not gotten to how I did the whole magical thing. This is, for now, a tangent. Is that okay? So let's try and follow this process to find numbers A, B, C, D, and E. Okay? So what we're going to do is repeatedly divide by 6 and take the remainder when we divide by 6. So first, let's see what happens when we divide 1344 by 6. I know it's going to divide evenly because the digits sum to a multiple of 3. Do they? Yeah, they do. 444, that's 12. That's a multiple of 3. And it's even, so it's going to divide by 6. Okay? But let's just do this. 1, 4, 2, 2, 24, and that's a 4. Okay? So what's the remainder when I divided by 6 here? 0. So I'm going to write a 0. Let me write a box here. 13. Okay. Well, let's write a 0 at the end of this box. And what's the result when I divided by 0? Or divided by 6? 224, right? So the result of integer dividing 1344 by 6 is 224. So now let's start with 224. Let's divide this by 6, okay? So what do we get? We get a 3, 18, 4, 4, 7, 4, 2, 2. What's our remainder? 2, right? So I'm going to write a 2 at the end of this. And what's the result of integer dividing 224 by 6? 37. Okay, so you can sort of see how this process is going to work. What do I do again? 37, divide that by 6. I get a remainder of 1, and my result was 6. So let's continue. Integer divide 6 by 6. My result is 1. What's the remainder? 0, so I'll put a 0 here. And now I'm left with dividing 6 by 1. Well, my result is 0. And what's the remainder? 1. So that tells me that 1344 in base 10 is equal to whatever this is in base 6. Is that clear? And so what you could do if you wanted to verify is plug in A is equal to 1, B is equal to 0, C is equal to 1, D is equal to 2, and E is equal to 0, and evaluate that expression, and you would get 1344 in base 10. Is that okay? And I know we're moving pretty quickly. Don't worry too much about this exact calculation because we will revisit this topic when we actually get to it in the course. This for right now is just to sort of help explain that magic that we had going on earlier. Sound good? Okay. So now let's revisit the problem. Like how did I do this magic? Okay. So notice I asked you 2 very specific points. I didn't just I didn't tell you to tell me 2 points because then it would be impossible. Right? Instead, what I did was I asked you for f of 1 and f of f at 1 plus 1. Is that clear? So for example, if you told me f of 1 was 5, I would then ask you for f of 6. Is that clear? That's why at the back, you said f of 1 was 10, then I asked for f of 11. Like here you said f of 1 was 15, I asked for f of 16. Is that clear? Okay. And there was an additional restriction in this problem. I told you that all of the coefficients had to be non-negative integers, meaning our polynomial couldn't have looked like 3x to the 5 minus 15. There were no minus signs anywhere in the expression. Otherwise, this wouldn't work. Okay? So by telling me f of 1, you actually told me the sum of the coefficients of your polynomial. So for example, if f of x is, x cubed plus 12x plus 1, f of 1, and our coefficients are, 1, 12, and 1, f of 1 just ends up being 1 plus 12 plus 1, which is 14. Is that clear? So f of 1 is just the sum of the coefficients. And since I know none of the coefficients are negative, I know that the largest possible coefficient is whatever the sum of the coefficients was. Is that okay? And that would be in the case where, for example, f of x was, a x to the n. In that case, the sum of the coefficients and the largest coefficient were the same thing. They would both be a. So for example, if your function was, 5x to the 10 or something, the f of 1, i.e. the number you give me, would be 5, and the largest coefficient would be 5. But in all other cases, if there's a plus sign anywhere, the largest coefficient will be smaller than whatever you tell me f of 1 is. Is that okay? Cool. So now, I know that the coefficients in your polynomial can actually be used to represent a number in that base. Okay? So, for example, if I know that the largest digit in the largest coefficient in your polynomial is 3, I know it can represent a number in base 4 or higher. Right? Because 133, for example, it can't be a number in binary, because in binary you're only allowed 0 and 1. It can't be a number in ternary, I guess, because in ternary you're only allowed 0, 1, 2. Is that clear? So the smallest base that this number could represent is 4. Is that clear? And by you telling me the sum of your coefficients, you're telling me, or you're giving me an upper bound on the largest possible digit I have in your set of coefficients. Is that okay? So essentially you're telling me what this 3 is. In this case, you would tell me 7, which is actually bigger than it needs to be. But for our purposes, this will work okay. Is that okay? So you're telling me what the largest possible coefficient on any of the terms in your polynomial is. Then, I evaluate f of b plus 1. Okay? Where b was whatever you told me f of 1 was. Okay? And I know it will end up looking like, a sub n, b plus 1 in the n, plus a sub n minus 1, b plus 1 to the n minus 1. This expansion looks awfully similar to this one, where we're just rewriting 1344 in base 6. Is that clear? So our problem now just boils down to rewriting f of b plus 1 in base b plus 1. But you already told me what f of b plus 1 was. And I know what b plus 1 is because you told me b. So I know this quantity, and I know each of these. So this is the same problem we had before, where all we have to do is this repeated division. So just by you telling me those 2 points, I can completely identify the polynomial. Okay, so let's work out an example, just to start from scratch. Okay, so suppose you tell me your polynomial, or you don't tell me that, but suppose your polynomial is f of x is x cubed plus 2x plus 3. Okay, and I ask you for f of 1, and you get 6, right? Because 1 plus 2 plus 3 is 6. Then I ask you for f of 7. Okay, so you get 7 cubed, which is 343, I think, plus 14 plus 3 gives you 360. So you tell me these 2 things. Or you give me all that information. Okay, now let's see how I can recover the polynomial from this. Okay, so now our job is rewrite 360 in base 7. Okay, so let's do it, just to sort of get some practice with it. So 360 divided by 7, get the 5, 10, 1, 7, 3. Okay, what's the remainder? 3. Okay, cool. And what do I get when I integer divide 360 by 7? 51, right? Because that's what we have up here. So now let's divide 51 by 7. And we know 7 squared is 49. And we'll have a remainder of 2. But our integer division result is 7. So let's move this over here. Now we have a 2. Okay? Now, what do we have? We want to divide, 7 by 7. What's the result? 1. And what's the remainder? 0. Remember, our base 7 representation, we only take the remainders, not the results themselves. So first we divided by 300, or divided from 360, then we divide from 51, now we're dividing from 7. Our remainder is 0, and that's what we're left with. And now, lastly, we're left with 1. So we try to divide 1 by 7. Our result is 0, and our remainder is 1. That gives us 1023. Well, 1023 in base 7 just tells us that our number looks like 1 times 7 to the 3 plus 0 times 7 squared plus 2 times 7 to the 1 plus 3 times 7 to the 0. Right? This is the ones column, the tens column, the hundreds column, the thousands column, but instead we're using 7 instead of 10. But that tells me that the polynomial itself is just f of x is x cubed plus 2x plus 3. And I can do that without even looking at the statement. I didn't have to write that down. You could have just told me these 2 pieces of information. Does that sort of make sense? I didn't use the fact that I knew this result at all. All I used was that I knew that f of 1 was 6 and f of 7 was 360. And then from that, I was able to recover the polynomial. Does that idea sort of make sense? Yeah. Because that was 1 greater than whatever f of 6 was, or f of 1 was. Okay? And it turns out I don't have to necessarily ask for f of 1. I could have asked you for f of 2. All I want is some guarantee that no coefficient in your polynomial is smaller than this number. Or sorry, is bigger than this number. Right? Because what if your polynomial happens to end up being like 99x to the 50 plus 32x to the 10? Okay? The smallest possible base that I could use to represent those numbers would be 100. Because 99 can't be in the expansion of a base 99 number or a base 98 number or so on and so forth. This example is a little weird because 99 in this case would be a digit itself, not the number itself. That's a weird example. I think there's a question back there.
Why did you use the remainder?
To create the base 7 expansion. I'd say don't worry too much about it right now. That's sort of how the process is. And later on in the class, we'll talk about where this comes from. For now, I sort of just showed it to you. Is that okay? So we just went through the entire process of asking for f of 1, asking for f of 1 greater than f of 1, rewriting this result in base this number plus 1, and that tells us a polynomial. Is that okay? Yes.
Wait, instead of like f of 7, you also just use anything bigger?
Yeah. I could have used f of 300 if I wanted to. All I have to do is make sure that this number is bigger than f of 1. Is that okay? Yeah.
If you use the number like greater than the actual number you're trying to make, like since we're using 1023,
Yeah.
if you use like let's say 1024,
Yeah.
how exactly would you make it with integers?
I'm not sure if I understand the question. Can you repeat that?
So like you said that like we can keep like we can use 300, we can use any bigger number than like the limit that we set, right?
Yeah.
So in that case, since the number is 1023 that we're trying to make, like we
Yeah.
used 7 to make it, what if we tried to use a number that was greater than what we were trying to make itself? Like you said 300, what if
Yeah.
it was 3000 for example? In that case, there's no way we can make it with integers, is there?
There is. So when I said 300, I meant... Okay, so I guess as a little background, when we're talking about hexadecimal, our digits, 0 through 9 look just like 0 through 9. But in hexadecimal, when we want a digit for 10, 10 in the traditional sense takes up 2 spots, like 2 text items in your computer, right? So they replace it with A. But it still just means the decimal value of 10. Is that clear? If we can go all the way till F, which is 15. When I meant 300, I was saying 300 could be some extension of these digits.
So you still have those.
Yeah. So it doesn't matter how large the coefficients in the polynomial are. All that does is it determines the smallest base that I can use for this. Is that okay? Okay, and again, I wouldn't worry too much if any of this is sort of seems unfamiliar to you, because we will revisit this trick later, and we will go significantly more in depth about how to rewrite numbers in certain bases later in the course. Okay? A couple more remarks regarding this, though. As I mentioned earlier, I could have asked for f of 2 and f of 2 plus 1. It didn't really matter that I asked for f of 1. All I wanted was some guarantee that the number you give me is an upper bound on the largest coefficient in the polynomial. Is that okay? If you plug in f of 10,000, you'll give me a large number, but I know that the largest coefficient in the polynomial is smaller than whatever that is. I just pick f of 1 because since I know all of the coefficients are non-negative, why not just pick the easiest thing to calculate? Right? Sometimes in the trick, if you try and search this up online, even though it's not that well documented, people say ask for f of 1 and then f of 1. Okay? And in all of the examples we just talked about, this will actually work. But there are a few counterexamples in which, no, I wouldn't call them counterexamples, but they're edge cases, and you sort of need to consider them separately. Okay? For example, if your function is, f of x is equal to x to the n, I ask for f of 1, I get 1. But with this version of the trick, I'm not gaining any more information by asking f of 1 again, right? Is that sort of clear? If all I asked was f of 1 and f of 1, it wouldn't give me any more information. But it turns out, since all the coefficients have to be non-negative integers, the only possible case for when f of 1 is 1 is when your function is of this form. So in that case, what you could do is just ask for f of 2, whatever it is, and take log base 2 of that. And that would tell you what the exponent n is. So for example, if you tell me f of 1 is 1 and f of 2 is 512, there's only one option, that your function is f of x is x to the 9. Does that make sense? Is that okay? But again, I wouldn't worry too much about this. And feel free to ask any questions about this. So to start to wrap things up, I thought it'd be interesting if we write code that actually takes in our 2 points and outputs what the guess of the polynomial is. Sound okay? Okay. And so our end goal is to have some function called guess, where I type in these 2 points. So for example, you tell me f of 1 is this, you tell me f of 16 is this, type those 2 things in, and it tells me what the polynomial is. That's our end goal. Is that okay? Cool. Let's take a look. So what do you think the first thing we need to implement is? What's the first thing we need to implement? Yes?
Can you tell a way to convert the f of b plus 1, f of b plus 1 into the base of b plus 1?
Exactly. The first thing we need to do before worrying about all this polynomial business is having a function that takes in some number and some base and returns the representation of that number in that base. Is that clear? And so what we'll need for that is essentially a function that does what we did here. Repeatedly integer divide by and take the remainder when we divide by. Is that okay? Okay. So, I don't have all this memorized, so let's pull this up. Why don't we get into it? Okay, so why don't we call it def change of base, and we'll take in our number n and the base b, and the return value will be an array. Okay, the reason, sure. Is that okay? Okay, so the return value in this case will be an array. Because what if we want to use base 11, for example? Then how do we represent the digit 10? I guess I could hard code that to be the letter A, but that just ends up being way more complicated than we need. All we really want is the values of the digits. Is that okay? So the return value should be an array. So can you think of a base case here? One where we wouldn't have to do any while loops or anything like that. Yeah.
0.
Yeah. If n is 0, all we need to return is a list with just containing 0. Is that okay? Because that's true in any base. So we know our return value will look like this array, digits. Okay? And what we want to do is keep on dividing n by b until n becomes 0. Is that clear? If we go back to the slides, I repeatedly divided until my result was 0. So what my while statement will be is while n is greater than 0. Is that clear? Yes?
What did you say n was supposed to represent again?
N would be, for example, like the number we want to convert, essentially. So the example we looked at earlier was converting 1344 to base 6. So what I could eventually do is say change of base 1344, comma 6, and I should get that result that we had before, 10120. Is that clear? Yeah.
Does this trick only work for converting base 10 to base whatever?
Yeah. Yeah, for right now, it assumes n is currently in base 10.
Okay.
Yeah. But if you wanted to implement one where you convert like from, I don't know, base 5 to base 12, what you could do is convert a number from base 5 to base 10, then 10 to 12. Does that sort of make sense? Okay. Cool. Okay, so while n is greater than 0, what do we want to do? Any ideas? Yeah.
You want to divide the number by the base and then keep track of both the integer division and the remainder.
Okay, good. So why don't we say the remainder, I'll call it REM, is just the result when I divide n by b. Is that clear? And that looks okay. And what I want to do is set n to be the result when I integer divide n by b. Is that okay? So what I'm doing is taking the remainder and then dividing by it. Okay? And what I want to do is keep track of this digit. Okay, so I can append the remainder. Yeah?
Why using an array?
Because, so what if my base was 12? Right? A potential digit could be 11. Right? And I just want each element in the array to represent a quote-unquote digit. Right? Because if our expansion had to look like a standard number, how would I represent 11? It would take up 2 digit spots. So that's why I want it to be an array. Is that sort of clear?
Yeah.
Okay. So that looks okay. Digits.append remainder. And this looks almost ready. Can anyone think of a potential issue we'd have with this? Yeah. Yeah, the array will be reversed. Is that clear? Because we're starting from the back and continuously adding to the back. So the order in which this would have been built in our code would have been 0, then 2, then 1, then 0, then 1. Is that clear? So what we need to do is reverse our list. And we can do that pretty easily just by trying that. Is that okay? So that looks okay. Oh, please work. I'll be sad if it doesn't. Okay, let's reload this. Okay. Okay. That's fine. Okay, and to test it out, change of base. Our previous example was changing 1344 to base 6, and the result should be 10120. Whoa, it works. Okay? So this function's okay. So most of the work is already there. Okay? So what I guess we can write is guess, def guess. The first version we'll write is one that takes in a function, function, I guess, if that makes sense. So what I could do is say def test of x. I can say return x to the 5 plus 13 times x to the 4 plus 99,000. Like, let's just see if it works. X squared plus 21. Okay? That'll be our test function. And what I want to do is write another function that takes in my function, calls it at these 2 points, and returns the best guess of it. Is that clear? Okay? So what I want is these 2 points. First, whatever the function is evaluated at 1, and then whatever f of 1 plus 1 is. Is that clear? Those are the 2 points we were looking at. And what we want to do is our coefficients can be the change of base, writing c in base b plus 1. Is that okay? This is a rehash of what we did essentially manually, right? We queried for f of 1, and then whatever f of 1 was, we added 1 to that and queried that again. Is that clear? So this is just asking for, f of 1, telling me that it's 15, then finding out what f of 16 is. Is that clear? And then what we did was we wrote this result, f of b plus 1, in base b plus 1. So that's what that's going to do for us. And I guess we can return the coefficients. But to make things a little nicer, why don't we write a quick function that formats the output nicely, just to add to the magic. Okay. So format output. Okay. So we know we want to return a string. So now what I want to do is return a string that looks like x, caret 5 plus blah blah blah. So it'll be a string representation of what the polynomial is. Okay? So what I want to do is go through my coefficient array, and the first coefficient, like so for example, if we have 1, 0, 1, 2, 0, what's the length of this array? 5. So we know it represents degree what? Right? It represents degree 4. So I know that this should be 1 times x to the 4. I should ignore the 0 because I need it's 0, right? Then plus 1 times x to the 3 plus 2 times, no, that should be 2. Plus 2 times x to the 1 plus, and then ignore that plus. Is that clear? So this is our goal now. Take in this coefficient array and return the string representation. It doesn't really matter, but I mean, it sort of adds to the magic, so let's do it. Okay. So what we can do is for I in range, the length of our coefficients array. Have they gotten to for loops in 61A yet? Just started. Okay. Hopefully this is not too foreign, but essentially what we're going to do is first set I to 0, then I to 1, all the way until the length of our coefficients array. Okay? And again, don't worry too much about this. Programming probably won't do very much of it at any point in the rest of the course. Okay, so for a coefficient at I is 0, we want to ignore it. And then otherwise, to our string, we want to add something x to the something. Okay? We know that that's what this is going to look like. Something x to the something. Right? And what we want to do is format, and we probably also want a plus and a space. And we can do some string formatting here. Okay? What should the first thing be? Well, that's the coefficients list at I, because that's what our this array tells us. It tells us what the number at the front is. Is that clear? Okay? What should the second thing be? How can I find the exponent? Yeah. Okay, so we can try length of coefficients minus I. So here, the length of the coefficients is 5. Here I is set to 0. That would give me 5 as the exponent. So I also need to subtract 1. Is that clear? So I need to take the length of my coefficients array minus I minus 1. Okay? And that should look okay. So we return out, but you also know at the very last term that we have, it will be plus space nothing. Is that clear? Because I'm adding this plus at the end of the output every time. So just to make it a little nicer, we can cut off the last few characters. Okay? So now we have this format output thing, and what we can do is say return format output of coefs. Yeah. Okay? So now we have our change of base function implemented, somewhere here. Change of base is implemented. The one that handles all our function logic is implemented. So now let's try it. So we said that test f is x to the 5 plus 13x to the 4 plus 99,000 x squared plus 21. Okay? So why don't we try it? So guess f of test f. And it tells it to you. Right? And what it does is it evaluates the test f at 1, test f at f of 1 plus 1, does the change of base formula, converts the output, and gives it to you. If we wanted to be a little more complete in this output thing, we could make it ignore the x to the 0. That doesn't matter a whole lot right now. But the last sort of step is the version where I don't even supply a function. It should be the one where I take your 2 points and it spits out the function. Okay, so let's try and write that. So why don't we say def guess from points. And you can tell me your first point and your second point. And all I want to do is return the format out. I guess we can do it a little more concretely. The coefs can be the change of base of b in base a plus 1. Is that clear? These names are misleading. I should call this b and c. Is that clear? So you're giving me your f of 1, which is equal to b, and then your f of 1 plus 1, which is your c. And my job is to rewrite c in base b plus 1. So I'm calling the change of base function, and then do the same thing, return format output of coefs. Okay, let's test this out. So guess from points. Let's see if I remember someone's example from before. Sure. So someone's example before was f of 1 was 10, and f of 11 was 1127390. Okay? And that was the function. So it does all the work for you. Okay, so we sort of implemented each step at a time. First, the change of base function, where we repeatedly did integer division and took the remainder when we divided by. And then wrote the format output, wrote a function that does the logic for us, both in terms of taking in a function as the input, and then also by guessing the points. So we can also even do, I don't think you've talked about lambda functions yet in 61A, but lambdas are essentially a way of defining an inline function. Those of you who took taken 61A, you'll know. But I can come up with any function I want. Why don't I try like x to the 10,000 plus 10,000 times x to the 99 plus 23. Should it work? Okay, yeah, it works. Cool. And the reason it's not that computationally intensive is because it's only doing this function call twice, right? So it does the function call twice, has all the information it needs, and then just jumps up to change of base. And that, in terms of big O notation, if that's something you're familiar with, is a linear operation, right? Because the beginning step will always only be 2 calculations because I'm only evaluating the function twice. And then when I change the base, it's an iterative process. For each, while the number is less than 0 or greater than 0, and there's only a finite number of digits, right? I keep dividing by n, or dividing by b. So it's a linear operation. So even though the exponents I chose were pretty big, I'm only really doing 2 calculations plus the act of changing the base, which doesn't take too long. So any questions with this code that we've written? And again, don't worry too much about following along with the code. We probably won't write very much code unless I think it's interesting and supplements the material that we have. Okay. So a question I want you to discuss with the people immediately near you. Introduce yourself, name, major, where you live if you're a freshman, I guess. Think about, does this violate the properties of polynomials? Okay? Remember, way back when, I told you that to interpolate a polynomial of degree n, I need n plus 1 points, right? But I just tried this example with the polynomial of degree 10,000, and I still identified it with only 2 points. When in theory, I would need 10,001 points to find that polynomial. Oh, don't look at the answer. Is that sort of clear? So discuss with the people near you as to why this does or does not violate, the laws of physics or something. Think about that for a couple minutes. Okay, let's come back together. Okay. So why does this or why does this not violate the principles of the universe? Yeah.
I'm going to say it doesn't. Because,
Okay.
By having those 2 special points, it allows you to do the, when you're converting to the base.
Yeah.
I think that maybe, you do the operation of modulus, 10 plus 1 times or something,
Okay.
and that gives you the points you need to think about.
Okay, that's an interesting thought. I didn't think about it like that. So what you're saying is, in the operation of rewriting 1344 in base 6, for example, we end up finding n plus 1 points.
Yeah,
Is what
you
you're saying.
somehow find that.
Interesting. Okay, I have to think a little bit more about that, but that is interesting. Any other ideas? Yeah.
Well, it's also like specific points.
Yeah.
So there's like the second point has like a goal behind it, which has to be larger than the greatest coefficient. So
Yeah.
it's like, I'll just end it.
Exactly. And so the reason it doesn't violate the laws of the universe, I guess, but the reason for that is because the points that I'm asking you are very specific. F of 1, well, that really could have been anything. You could have told me any non-negative, you could have told me f of 1, f of 2, you could have just picked a point and gave it to me. But the next point has this condition where it's evaluated at a value larger than the previous evaluation, right? It's not that you were just giving me 2 random points and me trying to interpolate that. That would be impossible, right? It's this very specific action that I'm doing of asking for this one specific point and then asking for this other specific point that itself is a function of the previous point, right? It's these 2 specific queries, which is not what the properties we discussed on the previous page really talk about. On the previous page, that was just for a set of arbitrary n plus 1 points, right? That doesn't apply to this case where we're looking at 2 very specific 2 points, right? And you're right in that the action of me specifying this second point from the first one gives me more information. Okay? And also, there's this website, rapidtables.com. You might have used it before. They have a base converter on there as well, where you can just pick the starting base, the ending base, and the representation you have, and it will convert it for you. We could have just used that as well, but it's not as fun as writing your own code, I guess. So any questions with this entire example? No? Okay. So I think that's it for today. On Thursday, we'll start actual content that makes up the basis for this course. Feel free to read section 1 and 1.1 and 1.2 in the textbook. They're linked on the website, but you really don't have to. We'll cover basically everything in class. Office hours are only going to start next week because we haven't really covered anything yet. So they'll start next Monday. At some point this week, my guess is towards the end of the week, permission codes will be sent out, Piazza and Gradescope will be set up, and Homework 1 will be released either on Friday or Saturday. Okay? And yeah, feel free to email if you have any questions.